We've talked about direct variation. The next kind of variation is an inverse variation. So with direct variation, we were multiplying. With inverse variation, there's division. It's in the form of y equals k divided by x to the power of n. K cannot equal 0, and just like direct variation, n has to be greater than 0 as well. With this, in inverse variation, I'm actually going to talk about the graphs first, just a little bit differently than how I did the direct variation. With an inverse variation, if I start off with 1 over x, so that's just a very general term in that my k is 1, we're just keeping it basic here. Notice here on my graph in the red that I have a vertical asymptote line, or a spot where the graph never actually touches. And that vertical asymptote line is along the y-axis. As you can see, the graph here in red is coming towards that vertical asymptote line, but will never actually cross it. And then it jumps over to that other quadrant in order to keep that graph going. Now, that n component can change to be, a different variable, so let's say x squared. So notice now in the blue, this is an x squared graph. So the biggest difference is if you have an x here and the n is odd, it's going to be in this form where it's in quadrant 1 and quadrant 3. If it's going to be an even, so the n is even, it's going to be in the form of quadrant 1 and quadrant 2. Now, if, for instance, you have like a -3, like I have here at the bottom here with the green graph, notice it just shifted the graph to the right. So that -3, or if it's a plus or whatever, it's only going to shift the graph left and right. So you don't necessarily have to worry about that. Again, with the blue graph, notice it also has a vertical asymptote line at y equals 0. So graphs of inverse variation have vertical asymptote lines at, not y equals 0, but x equals 0. And again, depending on the quadrant is going to tell you which direction, whether it's even or an odd with that n variable. Now, that's just talking about the graphs when we are looking at equations. This is similar to the direct variation, so hopefully this will come a little bit easier than what the direct variation did. And I only say that because we've been working with this enough that you might have a better idea. So for instance, if you were to have y varies inversely as the cube of x if y equals 5 when x equals 2, find y when x equals 6. Okay, this is again similar to the direct variation where it's set up as they give us the formula, they give us some numbers to find the k, then we have to plug some information in. So the first thing we want to do is we want to write our equation. So y varies inversely as the cube of x. So since we know it's a inverse variation, we have k over x. It says the cube though, so it's to the power of 3. So that's our first initial equation. So now we're going to use that next portion in order to solve for k. So we now have 5 equals k over 2 cubed. So I'm just going to reduce this a little bit. 5 equals k over 8. So I then need to multiply both sides by 8. So k equals 40. Now I need to actually solve for y. I'm going to use that inverse variation equation, so this k is going to come up in that general form of that inverse variation. So this is my equation. Now I just need to plug in that 6. So y equals 40 over 6 cubed. So y equals 40 over 216, which, noticing right there, that can reduce. I know for sure that they're both divisible by 2, but I'm pretty sure it can reduce a little bit more so. That reduction then is now y equals 5 over 27. And that would be my final answer. Again, that's all based off of our original equation that we found. In the green there, we had to plug our information in order to solve for that k. Then with the blue, the last part, we use that k value and the x value to find the true y value. Again, so we talked about the graphs in terms of what the shape they have, talking about the different quadrants, vertical asymptotes. They could also have horizontal asymptotes. And we've also talked about how to find inverse variations with story problems in which we need to find a y value based on the original inverse variation equation.